Hello there, dual credit calculus students. I'm going to create what I believe is and hope to be a really strong comprehensive review of not just this section here, 3.4, but all of the important information we've learned from chapter 3 so far. I'm going to add in a little bit of review information here at the end. And like I said, I hope this to be, and I really think it is, a really strong review of everything to give you a lot of deep conceptual knowledge here. So there's one important thing I want to start with before I dive into the next few examples. And I want to look back at points of inflection. It should hopefully go without saying that not just points of inflection, but also critical numbers have to exist at points where the function is defined. And so it talks about how a point of inflection is an ordered pair where a graph changes concavity, like up to down, down to up. And so one of the points I want to make here is that for points of inflection, f is continuous, I'll abbreviate there, and f is differentiable. Now, really, that should make sense because if there's no derivative there, there's no point of inflection, there's no critical number. And so, again, the function is continuous and differentiable at that point. And so, really, that also means that the function needs to exist at that point. And we'll see that pop up here in just a little bit. All right, so we've already seen example A, and I've looked at it here, and I'm actually going to change up example B here to a different type of problem. It says here, determine the open intervals on which, again, the graph is concave up or down, and state any points of inflection. So we're going to be taking a deep dive into the second derivative. Now, but a couple points that I want to make. First is I'm going to change up this function here. I'm going to make it a different function. Okay, so I'm going to change f of x. F of x is now this. It is now f of x equals x times the square root of x plus 3. Or again, we just look at that as x plus 3 to the 1/2. So a couple important points that I want to make before we continue. The first is 1. Sometimes derivatives are hard. And, maybe you don't have to jot these few points down, but sometimes derivatives are hard. There are a number of functions that we've looked at throughout these sections, and we're just going to realize here that some of these derivatives are really going to require some skills. I'll try to teach you ways in which you can make the simplification process a little easier, but again, it's just an important point. Sometimes derivatives are hard, and we can't get around it. And the second is that, it's important to use your calculator to verify some of the information that we're going to find here. And part of that includes getting a picture for what the graph is going to look like and confirming our results with what we see in the graph. So we're going to start by taking the first derivative of this function. All right, so I'm going to rewrite this as f of x equals x times x plus 3, x plus 3 to the 1/2. I'm going to be zooming here. Be sure to sort of try to leave yourself plenty of space for all the work we're going to do here. So take that first derivative. We're going to be using the product rule. So the derivative of x is just 1. And so that's going to be x plus 3 to the 1/2 for that first part. And then the derivative of x plus 3 to the 1/2, you bring that 1/2 down. X plus 3 to the negative 1/2 when you subtract. Derivative of the inside there is just 1. So we can really just leave that. It's probably best with all the writing we're going to be doing. The less writing, the better. But we can't forget to multiply it by that first function there, x. All right, so what I'm going to do is rewrite this. And I'm going to leave that as x plus 3 to the 1/2 here. And then over here, I like to just try to figure out what's on top, what's on bottom. You should really see there's going to be a 1x on top there. going to be a 1 and an x on top. And then that will leave us with the 2 and all this to go on the bottom. And so we have here on the top, we have x. And on the bottom, we have that 2x plus 3 to the 1/2 because it's now positive. So we're going to take that left side, and I hope that it's okay here to realize that since this denominator over here is 1, we can really simplify this process a little bit by realizing what we're going to do is just take that denominator there on the right and multiply x plus 3 to the 1/2 by that number. Now, what I'm going to go ahead and do here is just go ahead and add on that x from over here. Okay, and so that's really the entire numerator. And I think you can really help yourself out by trying to simplify while you're simplifying. And then we're left with that 2 times x plus 3 to the 1/2 power. All right, so that gives us a first derivative of, you notice you're going to take those x plus 3 to the 1/2 there in the numerator, okay? And that'll really multiply those together, and we've seen that before. That just ends up times x plus 3 plus that additional x all over 2 times x plus 3 to the 1/2. Don't go thinking you can cancel anything here. Not how it works. And so when you distribute, that's going to be, 2x plus 6 plus x. And, this is something that maybe you just kind of skip the writing, skip the step. I don't know. But then we end up with 3x plus 6 all over 2 times x plus 3 to the 1/2. And again, I know I've zoomed in here. On my paper, I've tried to take up as little space as possible with this. I want to make sure the writing is obviously very clear. But like I said, we're going to be writing quite a bit here. And so that's the first derivative, which we'll also see problems later. But you see in the grand scheme of things, I'm trying to leave myself plenty of space. But there's your first derivative, okay? So in order to test for concavity, we're going to need to take the second derivative. All right, now what I'm going to do here is when I go to now start taking the second derivative, we will be using the quotient rule. So derivative top there is going to be 3 times the bottom, and perhaps you just went ahead and wrote that as a 6. We'll do that here in just a moment. Minus the derivative of the bottom. So I'm going to take this 1/2 times 2 and just get 1. So it's going to be 1 times x plus 3 to the negative 1/2. And again, the derivative of the inside just being 1 times the function, the other function there, 3x plus 6. All over 2 times x plus 3, that whole thing to the 1/2, missing that there, squared. Now, I know that looks complex. Let's really think this through for a second, okay? So we need to figure out really where the second derivative is 0 and where it is not or where it does not exist. So really we're going to be looking at the numerator and the denominator. So at this point, it actually makes a little more sense to me to really just treat them separately. And so this looks like this really, maybe perhaps complex function here. Although if you look at the bottom here, that can really be cleaned up by really just squaring the 2 and multiplying the exponent there. That bottom can be cleaned up quite a bit. And the top here, we're going to do some simplifying with. But again, the goal is really just to find where the numerator is equal to 0 and the denominator is equal to 0. That's going to give us all the numbers that we need to test. So let's do just that. Okay, so what I'm going to do here is I'm now going to take that second derivative, okay, and I'm really going to now break it down. So I'm going to sort of just like, here's all my work there in getting the first and second derivative, okay? And so what I'm going to do now is take that second derivative and really break it down, okay? So we're going to take that numerator, all right? So I'm going to zoom in over here. You should have it down on your paper. All right, so let's find, where the second derivative is equal to 0, okay? So where's that second derivative going to be equal to 0? It's where the numerator is equal to 0. And so we're going to set this whole thing here. And so, back up, don't get too far ahead of myself here. 3 times 2 times x plus 3 to the 1/2 minus x plus 3 to the negative 1/2 times 3x plus 6, and then just that part. Again, we're going to set that equal to 0. Well, 3 times 2 here is 6. And then over here on the right, we end up with 3x plus 6 on the top, and then this x plus 3 to the 1/2 comes down here to the bottom. So again, I'm hoping that we can realize when I go to combine these, and I know this seems like maybe a lot of work here, but the more we see these types of functions, an important point I want to make here is that, especially when we're doing quotient rule on a variety of functions, and whether it's the first, second derivative, or both, we're going to see things like this happen a lot. Where, it's like you see this x plus 3 repeating, and it makes, I think, the simplification process a little easier. Like we see this x plus 3 to the 1/2, this x plus 3 to 1/2. That's not a coincidence. We've seen that multiple times before, so I'm hoping the simplification process gets easier for us as we're doing it. So what I'm going to do here is really come over here on that left side and multiply it by x plus 3 to the 1/2. Now, again, you can list really the top and bottom. I just sort of imagine only multiplying the top by it because I know I'm going to take those two fractions there and really combine them. That's the goal. And so when I multiply that out, we should get 6 times x plus 3 on the left. And then we're going to subtract this whole thing here, 3x plus 6. You got to be careful, subtract that all over x plus 3 to the 1/2. Now, I want you to remember here, okay? We're trying to figure out initially where this whole thing is equal to 0, all right? So you're like, well, I just ended up with another fraction again. So when we think about it, we're really not worried about where this part is equal to 0. We're actually really worried where this is equal to 0, because that would be undefined, that doesn't work. We're really just worried about now finding where this is equal to 0. So anytime where I can sort of ask myself, we can keep simplifying that, but is it necessary? No, it's not. We can save ourselves some time by now just saying, well, I'm going to take this top and distribute it, right? I'm going to take this negative and distribute it. So I want to know, where is 6x plus 18 minus 3x minus 6 equal to 0? That's really what I've found out. That's really all I'm interested in discovering. And so that's going to be 3x plus 12 equals 0. 3x equals negative 12, so x is negative 4. So we found one of those, I guess we could call it possible points of inflection, one of those points that we're going to use to test for concavity. And so, that's that part. Now we got to remember, we got to also figure out where is the second derivative, where it does not exist, which a lot of times will really coincide with where the function is not continuous, okay? So if you think back to our second derivative here, now we're going to figure out where this is equal to 0. And so again, especially if those algebra skills are pretty strong, then we can look at something like this and figure out where is this equal to 0. And again, make it, just take one step to simplify it pretty quickly. So if I'm taking all that to the second power, applying my exponent rules correctly, we could write that out, or realize that I just got to take 2 and square it, which is 4. And then when I square this like whole thing here, I'm really just going to take the exponents and multiply them, right? And again, you could write that out. 2 times x plus 3 to the 1/2 times 2 times x plus 3 to the 1/2, and see that. And see that you'd get really just 4 times x plus 3. And again, you could distribute, or realize really actually just divide by 4. Either way, they divide over that 4, it's just going to keep it at 0. So we get x is -3. Now, we have found these, points that we're going to test. These possible points of inflection. So now I got really that work over there. Okay. So now I'm going to come over here, and hopefully my work, I'm trying to keep my work sort of fairly organized here, at least in sections, so we can follow it. So really we got these like possible, POIs, right? And this isn't necessarily something that we have to write, but we got x equals -4 and -3. Now I want you to recall, here's a problem with a function like this. And we would probably realize this when we go to test it. But if you look at this function, and this is something that, it can be hard because we're really not programmed to think this immediately. But when we look at this function, and anytime we think of like a square root, essentially, we got to remember that there's really a restriction on the domain, okay? And if you were to graph this, you would, again, indeed see that the domain starts at -3, the domain of this function. And really all I got to do is set this part here equal to 0 to see that like the lowest x can be is -3. And so a note to make here is that for this function, the domain is -3 to infinity. It would kind of look like that, a closed and open bracket there. So really what that means is that we're not going to test, -4. It's not even in the domain. And if we tested points, I guess, to the left, right of it or whatever, we would quickly realize that. You would plug in numbers and get an error, and you would realize that there's really nothing for you to test there. So when we go to create our interval, like our test, right? When we go to now test it for its concavity, we're really just going to focus on -3. And, again, you could try that, like plug something in to the left, like a -4, or plug in something between -3 and -4. You would realize that everything over here just simply doesn't work, right? That it's not defined. And so, again, that would just reveal itself, when you go to plug in those numbers. All right, so wrapping up our test here then, we're going to test numbers to the right of -3. And we're going to see really that we should realize here that the concavity really isn't going to change. If it really just from -3 on, there's no other points where it could possibly change concavity. And so we won't end up with any points of inflection. That's hopefully something that we can start to think and notice here already. Okay, so let's finish wrapping up our test here. So we're just going to test 0, okay? And from there, we would plug that into the second derivative. And, this is something that when you go to take that second derivative, when you look at that second derivative, we have that 6 times 0 plus 3 to the 1/2 minus 0 plus 3 to the -1/2. And so 3 times 0 would just be 0 plus 6 all over. That would be 2 times 0 plus 3 to the 1/2 squared. So you can use some of the simplifying that we did to find those possible points of inflection to assist with this. And, 0 is obviously a little easier number to plug in here than others. Remember, the key is getting the sign of things. And so you plug all that in your calculator and you're going to get something positive. We're not really too worried about what the number is, but it's going to be positive. Now, specifically, I got approximately 0.577, but again, we're really just concerned with the fact that that is positive. So, since we know that the sign of the second derivative here is positive to the right there, we know that it is concave up, okay? Now, with it being concave up, I do want to point out, if we think about the graph of this for a second, if you do graph it, here's what you would find, okay? So what you would find is that you have a function here, and I'm just going to kind of list a few important points. So you got -3, 0, you got -2, -2, and 0, 0. So you got a few important points here where you got -3, -3, -2, -2, and 0, 0. It looks like this. It curves down, goes up. So you can see the concave upness to it. And that is it. There's no points of inflection. It just stays concave up the whole time. And so that makes sense. I mean, it verifies, matches up with everything that we have discovered here. So to give really our official final answer here, we would say that f of x is concave upward from -3 to infinity. Okay. And there, maybe it makes more sense to use a bracket there, but with these intervals, we're just continuing to use parentheses just to stay consistent with that. Since we know that the second derivative of x is greater than 0, or you could just say that it is positive on that interval. Now, it also asks about points of inflection, so we do want to answer that. We do want to say that f of x has no points of inflection since it never changes concavity. And that would finish our question. Okay, so now let's move into this next example. So we can see here that, again, this is going to be a quotient rule, and we're going to be using that a couple times. So let's dive into the first and second derivative and figure out where the, again, concave up, concave downness is, and any possible points of inflection. So let's start with the first derivative. All right, so first derivative, we're going to do quotient rule. So derivative of top, 2x times x squared minus 4, which is the bottom, minus the derivative of the bottom, which is 2x times the top, x squared plus 1, all over the bottom squared. Now, I am going to speed this up a little bit by recognizing the fact that there is a 2x here and a 2x there. So I can really simplify that top a lot faster than before by really just doing this. I'm going to take that 2x and factor it out. That leaves me with an x squared minus 4 here, and it leaves me with a negative that I'm going to go ahead and distribute here, and then that gives me negative x squared minus 1 all over x squared minus 4 squared, which leaves me with, you'll see that those x squareds cancel, and so you're just left with 2x by what is -5. And so times the bottom there. And again, maybe you sort of skipped this step. Negative 10x all over x squared minus 4 squared. So perhaps pause it here, see if you can find the second derivative and see what you come up with. I think, and I really hope that once we find the first and second derivatives, the rest of the work is a little bit easier. And the problem is we just can't look at these derivatives and try to assume too much on where the possible values might be. Okay, so let's go ahead and find that second derivative. All right, I'm gonna switch colors here. So second derivative of the top is negative 10 times the bottom, that x squared minus 4 all squared, minus the derivative of the bottom, so power rule with that chain rule, so you get just that to the first power times the derivative of the inside, and can't forget the other function. So that's definitely a lot there. It is, for sure. And so I'm just going to go ahead and put this as that to the fourth power. You got to be careful there. I think if it was a 3, then this would not be 5. I think just a random point I want to make. If say this was to the third, that would be to the 6th because there's 2 3s. And so you wouldn't, and I just want to make sure that that is a clear point. I know that's been something that I've seen a mistake made a few times. So seems wise here to try to clean it up a little bit before I try to do anything else. So what I'm going to do here is take that negative 2, that 2x, and that negative 10x, multiply all that together and get positive 40. Positive 40x squared, gotta be careful there, squared, times that x squared minus 4 all over that x squared minus 4 to the fourth. So here's again where I'm going to be factoring out some items, and I am going to factor out, you'll see here that this is like a negative 10 and a 40. So I'm going to go ahead and factor out the negative also. So between the negative 10 and the positive 40, I can factor out a negative 10. And you'll see that they each have an x squared minus 4. So what does that leave me with here? So when I take away the negative 10 and the x squared minus 4, it leaves me with just the x squared minus 4 there. Now what does it leave me with over here? Well, that's gone because I factored that out. So when I divide 40x squared by this negative 10, that leaves me with a minus 4x squared. Okay. And so from there, that would be, you'll notice that from there, this will cancel one of these, drops that down to a 3. So that would be negative 10. And then on the inside there, you get negative 3x squared minus 4 all over x squared minus 4 to the third. Now what I would go ahead and do is I'm going to leave that 10 on the outside because when you distribute it, you're just going to have to factor it out again anyway when you set it equal to 0. So that's just going to disappear when you set the top equal to 0 anyway. I am, though, however, going to clean it up and just notice that I can change all those to positives just to, maybe make working with less negatives, make it a little easier. So we have a similar situation to what we just had where we need to set both the derivative or set the numerator and denominator equal to 0 to get all of the possible points of inflection we want to test. And again, sorry, I had to just clean it up there a little bit. That's our second derivative. So now that we have our first and second derivative, what we're going to do is figure out where is the second derivative equal to 0. Okay, so we have all that work done to get the first or second derivative. We're going to figure out where is that second derivative equal to 0. And that would be where the numerator here is equal to 0. Now, I want to point something out. Anytime you can make things easier on yourself, do it. All right. And so you really got, if you think to yourself here, we can solve this, but I do want to point something out. Okay. Think about this. All right. This is obviously a positive number. Squaring anything will make it positive, and adding a positive to it, this will be a positive plus a positive times a positive. This is going to be positive. So it's never going to equal zero. So I could just stop there and say, oh, that's not going to equal zero. Let's move on. If you did continue, you would divide over that 10. You would subtract the 4. You would divide by 3 and realize I can't take the square root of a negative number. So all in all, we just know, okay, it's never going to be 0. So let's move on. So let's now go to where the second derivative of x does not exist. Now, for starters, you might be thinking, well, that's just a huge waste of time. No, because it confirms that there's no values where it's equal to 0. It's necessary information. It's not like we wasted our time, because it's probably more likely that we will get values there. So to assume that it's just not going to ever equal 0 would obviously be a mistake. So now what we want to do is we want to figure out where that x squared minus 4 is equal to 0. I left off the cubed part because we're really just worried about the inside of it. And so equals 4, so we should see there that that is plus or minus 2. So in the end, all that work, all those derivatives, and we discover that what we need to do now for our test is we need to test the values -2 and 2. So really 3 potential intervals here where we will see concavity, and then we come up with our values to test and go from there. So I am going to test here. I'm going to test -3. I'm going to test 0. And I'm going to test 3. So let's do that. All right. So what is the second derivative at -3? I'm going to show you all that written out. And I'll, again, speed up this process here a little bit, as we're finding the rest of them. So that would be -3 squared minus 4 cubed. You got to be careful with all those negatives, all those parentheses. Spit it all out, boom, 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 boom. You get 2.48. So the second derivative here is positive. And, keep in mind, this is probably something you want to go ahead and write. Like you want to go ahead and write second derivative here because, again, we're testing concavity. So you might want to do that. Just remember the problem in which we're in, okay? And you maybe even just write down here on the bottom concavity or something, just reminding yourself exactly what we're doing each time. You always want to be in that habit. Just the more you do it, the more often you'll get that right. So that tells us that the function there is, concave up in that interval. Okay, so continuing on, you find that when you plug in 0, you're going to get 40 over -64. And that is just going to be, again, it's going to be negative. And therefore, on that interval, -2 to 2, we know it is concave down, which tells us that -2 we think is a point of inflection. I'll tell you why I'm saying that here in just a moment. And then when I plug in f double prime there of 3, the second derivative of 3, we again get 2.48. And I will point something out. Notice that the only difference between plugging in -3 and 3 is this here, where you -3 and 3 squared are the same, and here -3 and 3 squared are the same. So it should make sense that when we look at it, when I change that -3 to a 3, I'm going to get the same value. And so that tells us here that it is positive and that it is concave up. So again, we think this 2 here is a point of inflection. I'm sorry there's not a lot of space there for the interval or the number line there, or a little test diagram. So we have everything we need, the concave up, concave down, we have points of inflection. However, and I say this till the end as a means to stress this because this is the habit you're going to get into. So there's a reason I say this for the end. We think -2 and 2 are points of inflection. Let's look at the graph here. We have the graph of this function, and we can see vertical asymptotes at -2 and 2. Don't forget one thing we discussed very often in this class, and that is variables in the denominator cause issues. And so we should see very quickly from this that it's not going to be defined at 2 and -2. Therefore, it is not differentiable. Therefore, -2 and 2 are not critical numbers. They're not points of inflection, okay? And so one of the things that we might want to then do is start thinking about all the way back up here at this function. We know that x cannot equal -2 and 2. So that rules out the possibility of them being critical numbers. And specifically in this case, they are not points of inflection. Okay? And so that rules out the possibility. They are, therefore, they cannot be points of inflection. And that means that while we think they're points of inflection, turns out they're not. I guess it's kind of like that idea of like an extraneous solution that you think x is supposed to be a number, but it turns out it's not a zero of say like a quadratic or polynomial or something like that. So, anyways, turns out now it doesn't change the concavity though, because that was confirmed by our test, by our second derivative test. Okay. And so we can still see concave up here, concave down here, concave up here. That is again all confirmed by graphing the function. So again, to give our official answer to this problem, my apologies. There we go. To give our official answer, we would say f of x is concave up from -infinity to -2 and to infinity because the second derivative is positive on those intervals. We would say f of x is concave down on the interval -2 to 2, since the second derivative is negative on that interval. And lastly, we want to state about the points of inflection that it has no points of inflection. Now again, our first 2 points there would lead us to believe that it does have points of inflection, that being the fact that it's certainly changed concavity. But the problem is that it has no points of inflection since f of x is not defined and therefore not differentiable at x equals -2 and 2. And we are done. Okay, so this brings us to the second derivative test, which you will see is a means for us to check for relative minimum and maximum. Now, I know we've already had this before with the first derivative test, where we look to see if the derivative was changing signs to determine relative minimum or maximum. So I want to point out a few important things here before we dive into this. First is you'll find, I think this example will be very comprehensive of a lot of different ideas. And the second is that while we are going to use the second derivative as a means to check the sign, I want to point out that it talks about the fact that this is where the first derivative is equal to 0. So we're going to really start by finding both the first and second derivative, but we're actually going to test where the first derivative is equal to 0, and it says the second derivative must exist. And, if the second derivative doesn't exist, I doubt the first one does. And so, we're going to really check to see where the first derivative is equal to 0, but then use those numbers to check their signs at the second derivative. Now notice this as well. It says if the second derivative is equal to 0 at that point, then it turns out this test is inconclusive. It still may be a relative extrema. We're going to have to go back to the first derivative test. So it's going to really combine a lot of different things. I do want to make this important point. Why is it that we're using the first derivative, where the first derivative is 0, but the second derivative, and why is it just simply whether it's positive or negative, not about changing signs or anything like that? With the first derivative, it had to change from negative to positive. Here it just wants to know the sign. I want you to think about this for a second. This is really important, okay? Think about this. All right, I'm going to just talk about this point here for just a second, just this one. All right. If the second derivative is positive, why is there a relative minimum? Here is why. Okay. If f goes from decreasing to increasing, that's going to be a relative minimum. Yes, decreasing to increasing. This means that the first derivative goes from negative to positive. Yes, that's what we know. That's how the function and its first derivative relate there at that minimum. If you look at the graph of a function and its derivative, you'd see at the relative minimum, that point is where if you graphed the derivative, its function graph would change, or the first derivative graph would change signs. Now, if the first derivative is going from negative to positive, the only way that's possible, think about just a graph going from negative to positive. You have to be going up, right? So this means that the first derivative is increasing at that point. It's got to be going up, because if it's going from negative to positive, that's the only way that's possible on a graph. And if it's increasing at that point where f prime of x is equal to 0, right? So starting over, it says f goes from decreasing to increasing. That means the derivative goes from negative to positive. This means that the derivative is increasing at that point, right? So let's kind of write it this way. If f goes from decreasing to increasing, the first derivative goes from negative to positive. This means the first derivative is increasing at that point where the derivative is 0. So if the first derivative is increasing at that point, it means, using the same logic going from a function to its derivative, that the second derivative will be positive as necessary, as we can see here in this point. Therefore, if this really all starts back at the fact that the function's going from negative from decreasing to increasing, a relative minimum, it follows, right? If the second derivative is positive, then we're going to have a relative minimum. And similar reasoning could be used for 2 there. You just flip a lot of the decreasing to increasing, negative to positive and stuff, and you'd have a similar explanation. So really important point there to actually understand. All right, so let's look at the example. So what are we going to do? We're going to start by finding its first and second derivative. Just get both of those out of the way. So where's the first? The first derivative is negative 15 x to the 4th plus 15 x squared. What is the second derivative? The second derivative is negative 60 x to the 3rd plus 30x. So what am I going to start with? I'm going to start with actually setting the first derivative equal to 0, right? Look at the second derivative test. We're going to take the first derivative set equal to 0. Remember, the question, what does the question ask us? Probably should have started with that. Find the relative extrema. And it says using the second derivative test. So we got to start with where is the first derivative equal to 0. Where is negative 15x to the fourth plus 5x squared equal to 0. Where is that equal to 0? All right. So solving this here, we're going to factor out a negative 15x to the second, and we're left with x squared minus 1 equals 0. So setting both of those, we know that first part here, that's just going to be that's just going to be 0. Anytime we have a constant, just like a monomial there, we know that x is just going to be 0. And we should see inside there that's going to be plus or minus 1. So we have all our points that we need to test. Now, I'm not going to treat this like an interval because we're not going to be testing like different values between those. I'm not going to treat this like a number line. I'm more just going to create a table, okay? So I'm just going to create a table here with those values. So I'm going to do it like this, okay? And you see something similar like this in your book. I really think this is really just the best way to go. You could come up with your own, strategy here, however it is you want to do it and organize it. I'm going to start over here, zoom in a little bit, save some space. So we're going to take those values there, that 0, negative 1, 1, that's where the first derivative equals 0, and we're going to organize it like such. We're going to test specific points. We're going to figure out what is the sign of the second derivative at that point, and therefore what is the conclusion that we can make from that, okay? And so what are the points that we are going to test? We're going to test 3 points. That's going to be where x is negative 1, 0, and 1. Probably want to list those in order. Now you'll notice that we can save ourselves some time because when we talk about relative extrema, and this is something I'll summarize here at the end of the video, we just want to go ahead and have the x and the y value. So we're going to go ahead and plug all of those values into the function. And again, I'm going to save a little bit of time here in the video and show you just initially how I'd set up some of these and give you the rest of the numbers. Use your calculators properly, write it all out. Okay, so we're going to plug these into the function, by the way. Notice how I'm plugging this into the function, the original function up there, that negative 3x to the fifth plus 5x to the third, because I want to find the y values of the function, the relative extrema for the function. Not first derivative, second derivative, the function. So I'm going to plug negative 1 in here, negative 3 times negative 1 to the fifth plus 5 times negative 1 to the third equals negative 2. Okay, I'm going to go ahead and give you the values here. This is 0. This is 2. So we have all our points. Let me clean this up here just a little bit to give us some more space. A little more clear. It's going to be negative 1, negative 2. So we got negative 1, negative 2, 0, 0, and 1, 2. So what we're going to do is check the sign of the second derivative. So now what I'm going to do is plug those same values into the second derivative. And again, speed up the video here just a little bit. So where do we want to plug those into? That would be negative 60. You notice up there, our second derivative, negative 60, x to the third plus 30x. So it's going to be negative 60 times negative 1 to the third plus 30 times negative 1. And there you get 30. Here you're going to get 0. And again, that's a problem, right? 0. So we're going to have to go back to the first derivative test. And here we get negative 30. So what does that tell us? It tells us that the sign of the second derivative at -1 is positive, which tells us that it is a relative, look at up there, it's a relative minimum. Relative minimum. Here we got 0, which meant that really, I'm just going to kind of put a question mark here for now. And at 1, we got negative, which meant this was a relative maximum. Okay, so we know we have most of the information we need to answer the question. We just now have to figure out this problem where it is 0 because we don't know. So I'm going to have to go back to the first derivative test. Okay, so now continuing on here, I'm going to have to go to the first derivative test. So what I'm going to do is I'm going to make my little number line. I'm going to first make a note, the first derivative test. I'm checking the first derivative, and I'm going to have to check that at 0. Now, where you want to be careful is with this is that while you're checking numbers to the left and right, you got to be careful because we're really interested, while I'm only looking at 0 here, I do still need to remember that I'm checking really not only 0, but really in that -1 to 1 range, right? So I'm really trying to figure out what's happening over here and what's happening over here. Does it change from negative to positive or positive to negative? Because that's going to tell me using the first derivative test if the first derivative changes signs. So I have to come up with a number to the left of 0 and right of 0. Now you might be tempted to try -1 and 1, and you're going to notice that that would be a problem, okay? Because you're going to end up getting, you're going to end up getting 0 because you know that those are the numbers you initially found using the first derivative. It's not going to tell you anything. So the issue with that is that you want to be careful because we want to test values really here. So I'm going to test -1/2 and 1/2. And we're trying to figure out, does the first derivative change signs? So let's do that. What is f of f prime, the first derivative of -1/2? Looking now I'm plugging numbers into the first derivative. So you notice through this process, I plug numbers into the function at times, then the second derivative, now the first derivative. And that's going to be -15 times -1/2 to the fourth plus 15 times -1/2 squared, which is going to be positive 45 over 16 when you change that back to a fraction. Really, we're just worried about the fact, again, that it is positive here. Now, we should hopefully notice when I go to plug into the first derivative 1/2 that we're going to get the same number, and that's because, again, -1/2 to the fourth and 1/2 to the fourth, since those are even powers there, are going to get the same number. And indeed, we do. You end up getting 45 over 16 again, but it is the big concern, big takeaway here is that it is positive. What that tells us is that it doesn't change signs. We know that it is increasing and it stays increasing, and so it doesn't change signs. Therefore, it is not a relative min or max. So what that tells us is that f of 0, which we know is 0, 0, right? So it tells me that 0, 0 is not a relative min or max, right? And so we know that is not a relative min or max. So that really gives us our final answer. Here we know that it is neither, okay? And so we can fill that in. And that gives us enough information to finish the question. Okay, we can then say that using this information, we know that f of x has a relative, and you can abbreviate there, relative min at -1, -2, because the second derivative is positive and a relative max at 1, 2, because the second derivative is negative. And there's our final answer. Now, a couple points I do want to make here real quick. If you were to graph this, okay, you would confirm everything that we just discovered. Okay, so I'm going to just draw a quick rough sketch of this graph. And part of where we are headed here is we're headed towards this idea of how can we sketch different functions by knowing all the information, like where is its min, max, points of inflection, concave up, down, increasing, decreasing, combining all of this together to actually come up with a graph of a wide variety of types of functions. So if we take the points -1, -2, 0, 0, 1, 2, we got to figure out, well, it's x to the fifth. And this is another thing to think about. If it's x to the fifth, we should know that it starts up here and ends like somewhere down here, right? And so combining that, how is that going to happen? Well, is it just like a nice sort of smooth curve like this? Turns out no, because we've got to remember that 0 is not a min or max. And so what ends up happening here when I graph this, this is a very loose sketch. So it turns out, remember, that -1's got to be a min, and it makes sense because we know that the graph has to start up here and it's going to end down here. So it's going to have to go back up and back down at some point. Now what happens at 0 is that it kind of has like it quickly has a derivative of 0 and then changes and goes back down like that. And so that is why, as you can see there, it's confirmed that it's not a min or max. It just stays increasing, which again, we'd use the first derivative test to confirm that it starts increasing and it stays increasing and then goes back down. It all connects. Now, another point I wanted to make here is that if we were going to continue this and check for concavity, so we've used we used really first and second derivative test here. I do want to talk about the concept of concavity real quick. If we were going to test for concavity, what we would do is we would want to figure out where is that second derivative equal to 0, right? If we were going to test for concavity, where is that second derivative of x equal to 0? Okay? And so what we would do, and also undefined, but we can clearly see here that that's not an issue. We would take this, set it equal to 0. You'd get -30x times 2x squared minus 1. And you could see from the outside part there that you're going to get 0. And the inside part, you'll notice when you add 1, when I take this and set it equal to 0, I get 2x squared equals 1, x squared equals 1/2. So it's going to be plus or minus the square root of 1/2. So basically, if we were going to test for concavity, we would take our second derivative, okay, and we would check the sign of the second derivative at, insert within certain intervals. That being, well, this is negative square root of 1/2. This is 0. This is positive square root of 1/2. We'd look at the signs of the second derivative and then, go from there. I do want to state that this is just extra content I'm going over with this problem, really just to continue to show you how first derivative, second derivative, first derivative test, second derivative test, all of it relates to each other. That will wrap up the video here. I know that was a lot to watch, a lot to take in. I really do hope that this was beneficial and you took a lot away from it. And we will continue to review this in class next week. And let me know if you have any questions.